Okay, so good afternoon, everybody. Buenas tardes. Hope everybody had a good week. As a reminder, if you could go to the Google Classroom page, which you can see on my screen, there's a notification on the stream page about the Python tutorial for week 3, or alternatively, you can go to the classwork tab and scroll down to week 3. And if you click on that, you'll see the link to the file for this week in Google Colaboratory. You just want to click on that. I'm not going to click on it because I already have it open, but if you click on that, it will open up. Where is it? You will open up this week's Python tutorial in Google Colaboratory. So that the title should be week 3. And then I'll just give everybody a moment to do that. And so as a reminder, when you open up the file, the first thing you want to do is you want to come up to the top menu under File, and then Save a Copy in Drive. Okay, so just make sure you're saving a copy in your Google Drive, and that will allow you to edit the file and to run all the sections without any issues. Okay, so again, open up the file. It'll look like this. Come up to the File menu at the top of the screen on the far left, and come down and save a copy in Drive. Okay, and that'll open up, so it won't work for me, but it'll open up a new tab with exactly the same file, except that the title will say copy of, and then the name of the file, Satellite Monitoring Smoke Fires Week 3. Okay, so you want to work with that copy. That's actually the version that's saved in your Google Drive. All right, does anybody have any questions before we get started? Everybody pulled that up okay? All right, so just to tell you kind of where we're going this week, what we're going to be working on, is so specifically this week, we're going to be working with the VIIRS Level 2 aerosol optical depth and the VIIRS files, which if you remember, those are called active VIIRS, or AF for short. So what we're going to do in the first section, we're going to focus on those VIIRS files. We're going to do a little review. We're going to actually download data files from the JPSS NOD, that open NOAA Open Data Distribution Cloud Archive that we did in week 1. So that'll be a review. We'll actually re-download those files. Then we're going to open up one of the files because every time you work with a new satellite product, you just want to make sure you understand the structure of the files. So we want to open up one of the files and look at the metadata for the whole file, and then look at the data variables, make sure we understand what the data variables are that we'll be using. The VIIRS files have an optional organizational structure, and we'll talk about that. It's called groups. And then with the VIIRS files, the package we're going to use, Xarray, the Python library, will let us open up all 10 of the VIIRS, individual VIIRS files at one time. So we'll talk about how to do that. Then we're going to make 2 plots. Let me show them to you. So the first plot we're going to make is we're going to plot the fire detections. So that's just the locations, the latitude and longitude of the fires sensed by VIIRS. And again, we're working with November 6, 2023. That's our case study event day for the whole course of the training. And remember, last week we learned how to make a figure with that map tiles background. So we're going to plot the fire detections on that map tiles background. It's the Esri World Topographic Map. Okay. And then we're also going to plot on that same background, we're going to plot the fire radiative power. So if you remember, fire radiative power is a measure of the intensity of the fire. So that the higher values of fire radiative power, these darker orange colors, that indicates a fire that's burning more intensely or hotter. Okay. So let me close those. And then we're going to, in the second section, we're going to work with the AOD files, the aerosol optical depth files. So again, we'll go back and we'll review a little bit from week 1. We'll download the files from the JPSS Cloud Archive, the NOD. Just like we did with the VIIRS files, we'll open up one of the AOD files because we have to understand, what the contents of the file are. And then we're going to plot the aerosol optical depth data. So again, remember last week we saw how to make a map figure that has that shaded background with the land and the borders. So we're going to plot the VIIRS, the level 2 aerosol optical depth on that shaded map background with the latitude and longitude lines. And again, you'll see this is a little bit different. So if you remember last week, I think I still have it here. Yeah, if you remember last week, we plotted the VIIRS, the level 3 data. This is the plot we made last week. So if you remember, this was we downloaded one file and it had the global aerosol optical depth data gridded to 0.1 degrees resolution. And we just plotted the data over the Western Central South America. You can see how it's pixelated. These little pixels, these little squares look quite large. And so we can see that compared to what we're going to plot this week, which is the level 2 data, which is much higher spatial resolution. It's 750 meter resolution. So the coverage is a little more sparse, but the individual pixels have much higher spatial resolution. Okay. Does anybody have any questions before we get started? Okay, great. Okay, so I think I already mentioned this in the first week, but I just want to re-emphasize it. Anytime that you work with a new satellite product, the first thing you want to do is you want to find the documentation from the science teams. This will be something like a user's guide. Sometimes it's called a README document. If you really want all the details, you can read the algorithm theoretical basis document, which is called the ATBD. But usually you want the user's guide or the README file. You want to start with those. And those will tell you important information about the products, things like the valid data range, any sort of screening or filtering or processing you need to do of the data with quality flags, or any known issues about the product. So you definitely want to start there. So I have links to all of the NOAA polar orbiting satellite products, the JPSS products. And then also on my training webpage, I have links to all of the documentation for the aerosol optical depth, and then the VIIRS FIRE products we're going to work with today. Okay, so you don't have to read those right now, because the tutorial I'll tell you what you need to know, but I just want you to realize that those are resources for you, and that if you're working with a new product, you always want to read the documentation first. Okay. All right. So so the next section is the same as the last 2 weeks. So we need to set up Google Colaboratory. So this week we're going to work with, I think, all the same packages we've worked with before. I don't think there's any new ones here. So in terms of the modules and the libraries. So just as we did in past weeks, we have to install the S3FS, the NetCDF4, and the CartoPy packages. So let's go ahead and let's do that. And again, that'll take usually about 30 seconds or so to install. Remember, you'll see some warning messages about conflicts with the package dependencies, but we can ignore those. They won't impact us in the tutorial. Okay. All right. And then once we've done that, we've installed those packages, we can go ahead and we can import the modules and the packages that we'll need to use for today's tutorial. Okay. And they're very similar. I think they're, like I said, I don't think there's anything new. I think they're exactly the same as the ones that we've used in weeks 1 and 2. Okay. All right. And so just like we've done for the last 2 weeks, let's make some new, folders or directories on the Colab instance. So again, if we click on this little file icon here on the far left, we can open up this little menu bar here on the left, and we'll see we just made 2 folders or directories. We made one called VIIRS files. That's where we're going to put the files that we download. And then we've made one that's called map plots. That's where we're going to put the maps of the VIIRS and aerosol optical depth data that we make. All right, so I'm just going to make that a little smaller. And then as with the past 2 weeks, I like to name the paths to my directories just for convenience, just to make it a little bit easier. Okay, all right. So next we're going to have a brief review of what we did in week 1. Okay, so you remember we worked with the NOAA JPSS NOD S3 buckets. So you remember just here, those are the names of the buckets. And so the first thing that we have to do is we have to connect to the Amazon Web Services S3, the simple storage service. So let's run that. Okay. And then you remember that the polar orbiting, the JPSS S3 buckets don't have any sort of tool or interactive way to subset the global files. For each day, all 1,000 or 500 global files are in one directory. So we need to run this function here that I wrote. Let's just run it. We won't get any output from it. And this will actually subset or help us subset the data. Okay. So now, and again, this is a review from week 1. So now what we're going to do is we're going to, for the NOAA 20 satellite for November 6th, 2023, and then for the geographic domain set by these boundary corners for Western, Central, South America, we run this, we're going to find the times when the NOAA 20 satellite entered that domain and exited that domain. Okay, they're right here. And we're going to use those times in the next section to help us subset the VIIRS files on the JPSS node. Okay, all right. So again, this is still a review from week 1. So now let's actually, if I scroll down, the first thing we're going to do is we're going to actually get all of the VIIRS active fires I-band files. So again, these are the fires, the level 2 fire product from VIIRS from the NOAA 20 satellite. All right, we're going to get there's about over 1,000 files for each day. So the first thing we're going to do in this files variable that we're defining, we're going to use the F3SS package, and we're going to grab all 500, well, the names, the directory paths to all over 1,000 of those files. Okay.
Hi, Amy.
Yeah.
There was
ahead.
a comment on the chat that, maybe in case others had that issue.
Yes. Yeah, I mentioned that, so maybe I wasn't clear. So let me scroll up. So so if you see this bolded text here, and I did mention it, so we saw this last week as well. So you can ignore all these messages. So they're essentially just related to conflicts in the packages that we've installed and the packages that are already on the Google Colab installation. So they won't impact our tutorial, so you can ignore them. Yeah, we saw the same thing last week and then in the first week. Okay, so just, you can ignore those. They're not going to bother us. Okay, yeah, thanks, Anna. Any other questions?
I don't see any.
Okay,
Unless anybody
great.
has something.
Okay, so I think we were here. So what we just did is we grabbed all 1,000 plus files, NOAA 20 VIIRS active fires files for November 6th, 2023. And now we're going to use that function that I wrote. We're going to use the times when the NOAA 20 satellite entered and exited the Central, Western, South America region, our region of interest, and we're going to subset the files. So if we run this, let's run those. And then we printed out the file names. If you remember, we printed out the file names here, and then we printed out the approximate size of the files. Because before I download anything, I just like to make sure that I got the files that I wanted, and I like to check the size of the files before I download them. Okay, so this looks right. This is the same thing we found in week 1. So now we can use the fsget command, and we're going to download each of the files to that VIIRS files directory that we created. So if we run this and we open up this file, we'll see, or folder, we'll see that, and that should just take a second or two. I pulled this all the way out. So everybody should now have 10 of these active fires I-band files, net CDF files downloaded to their Google Co-Drive, Google Colab. All right. Everybody able to do that? Yes. Okay, super. Okay, so again, hopefully nobody's having problems with this. This is a review of week 1, okay, up until this point. I'll just give everybody a second, make sure nobody had any problems. Amy, why is it 10 files? Okay, so remember, we covered this in week 1. So remember, actually maybe a visual will help. Let me try a visual to see if this will help people. Hold on, give me a second. I'm going to pull up the NOAA JSTAR mapper. Let me go back to November 6th. So I can show you the individual files. Okay. Let me zoom out a little bit. Okay. So hopefully you guys remember from week 1 that the VIIRS, the level 2 files, both the aerosol optical depth and the VIIRS files, they're broken up into these individual little, they look almost like rectangles. They're called granules. So each of these little individual, as I highlight them, these little rectangles are individual data files, okay? So when we go to the JPSS node, we're getting all of the files, all of these individual granules files, but we don't want to download all of them, right? We just want to download, if I zoom in, we just want to download the files that fall over the central western portion of South America, right? That's the area that we're interested in, okay? So what we did is we used that function that I wrote to subset the files. So we just got the 10 files. They're roughly 1, 2, 3, 4, 5. So they're roughly about here to here, those files. There's 10 of them that fall over that geographic domain. Okay, so we identified those 10 files, and it's not each day the where the files fall will be slightly different. So it won't always be 10 every day, but you know, it'll approximately be probably anywhere from 8 to 12 files that will fall over, depending on the satellite and the day, that fall over that region. Okay, does that make sense? Okay, Odon says yes. Okay, great. I just want everybody to remember what we're doing, why we're doing it. Let me get the tutorial file back. Okay, so we just want to download the files that correspond to our geographic region of interest. Okay, good question. All right, so the next thing we're doing now is we're going to open up one of those files. So is everybody clear up to this point? I don't see any more questions. Okay, and you can feel free to ask your question in Spanish because Anna can help translate for me. Okay, Ana Prados. Okay, so now what we want to do is we want to, as I mentioned before, we want to take one of those files. We're going to take the first file and we're going to open it up and make sure we understand the data variables that we need to work with. Okay, so remember, like I said at the top, you want to make sure you read the documentation from the science team. So I've already read the user's manual. So I know that there's no recommendations for screening any of the FIRE pixels. So most of the time with satellite data, with the level 2 satellite data, there's quality flags that you need to use, and you only want to select the data pixels that correspond to specific quality flags. But the VIIRS team recommends using all of the FIRE pixels. So we're not gonna do any screening today for the FIRS. We will do screening for the aerosol optical depth. Okay, you'll see that in a second. And next week when we cover the ABI FIRS, we'll screen those files. But for the VIIRS FIRS, we don't need to do any screening. Okay, but we still want to open them up and take a look. So first thing we're going to do is we're just going to use the pathlib module, and we're going to just set the full directory path to the one of the files we downloaded. Okay, so let's run that. And then we're going to use, this is the command xr open dataset. This is the Xarray open dataset function. Okay, and we're going to point to the file directory, the directory path that we set. We called it file ID. And we're going to use the netcdf4 package. That's what this engine netcdf4 means. Okay, and then, and again, remember DS stands for dataset. This is the same Xarray function that we used last week. And then if we type DS, it will print the metadata for the file. Okay, so if we do that, we'll see a few things. First of all, this looks different from the level 3 file that we looked at last week. So normally when you open a file with Xarray, you'll see dimensions, you'll see coordinates, you'll see data variables. Data variables, that's where the actual data in the file is usually located. And then you'll see indexes, but these are all showing as 0. Okay, does anybody know what that means? Has anybody worked with satellite files before? Okay, what it means is that the satellite file is organized using an optional organizational structure called groups. So I'm going to I have a link here. I'm just going to click on this link from my documentation. I'm just going to show you. So this is just a link to, this is the netcdf4 file structure. It's just a schematic of it. So you can see here in the middle is a box called group. Okay, so group, and it's kind of, it uses red text because it's optional. So not every file uses groups. It's just like a subdirectory on your computer. It's just a way of organizing the data variables, which is what we're actually interested in the file. So if you see, I'm going to go back to the Python code now. If you see, when you open up a file, you see where it says data variables and it says 0. That means that the file is organized using these groups. Okay. So before I go on and I explain that, I just want to point out where it says attributes. If you click on the little arrow next to attributes, let me scroll back up. This is where we have the global metadata for the entire file. And so if you click on that, so again, it was just a little arrow next to attributes. And then you scroll down, you'll see there's just lots of information about the file itself. So, the satellite, the name of the sensor, so it's NOAA 20 VIIRS, the product, it's AFI band. And then it tells you some different information about the file. It'll give you information about the VIIRS bands that were used to make the file, all sorts of, different information. Okay, so just be aware, if you're interested, you want to know, the information about the file as a whole, it's going to be listed under this attributes section. Okay, all right, so so we need to do a workaround basically, because the Xarray package currently doesn't have a way to read the groups. Okay, so they're working on a fix to that, the Xarray developers, but until they have that fix finished, we have to do a workaround. So what I'm going to do next, I'm just closing that data set we opened, that file we opened right here. And the reason why is every time you open a file or a data set with Xarray and you're done with it, it's just a good idea to close it before you move on. That just, it's just good practice. It frees up the memory and, it's just a good thing to do. Okay. So, so I have mentioned here, so Xarray, it can open the individual groups in the file, but to do that, we have to know what the names of the groups are. But as I mentioned, Xarray won't display those names, so we need to use a different method to open up the file to see what the names of the groups are. So there's different ways you can do that. What I'm going to show you how to do next is to use the netcdf4 package to open it up. netcdf4 can read the group's names. And there's also, NASA has a tool called Panoply, and I have a link to it right here. Panoply is a nice tool. You can just download it right from the NASA webpage, and you can use that to open up netcdf files as well. Okay, so let me just show you. So here, we're going to use the dataset constructor of the netcdf4 package. And again, the file ID, that's just pointing to the file on the Google Colab instance. So if we run this and we print the metadata, okay? So you'll see at the top, it's showing all the same global metadata, the metadata for the file that we saw with the X-ray package. The difference is if you scroll down to the very bottom, you'll see the list of the groups. So it'll say groups, and then it'll have this file has 3 groups. So there's the group names are fire mask, fire pixels, and metadata for OSPO monitoring tool. Okay. So all we need is we just need these names, and then we can go back to X-ray and we can use X-ray to open the groups by name. Okay. Does that make sense, everybody? This is kind of important. Not all satellite data files have these groups, but when they do, you just need to know how to handle them.
Yeah, okay. Maybe you can pause for a second just to make sure everybody's, caught up. Can everybody indicate if they're, they want anything repeated or everything's okay? You can just put okay in the chat. Si pueden indicar todo está bien o necesitan alguna aclaración o están más bien, o todo está bien.
I see thumbs up. Okay, hasta claro. Okay, great. Okay.
Muy bien.
All right, looks like everybody's okay. All right, gracias. Okay, so now that we're finished with the NetCDF4 package, so let's close the file that we opened with NetCDF4. Again, this is it's good practice to do this. Okay, so now what we're going to do is we're going to go back to X-ray, and so we want to open the fire pixels. So the fire pixels group has all of the actual fire detections in it, the latitude of the sensed fires, the longitude of the fires, and that fire rated of power variable. All right. So what we're going to do, and we see it's fire pixels. So capital F, capital P, and there's a space between fire and pixels. Okay. So what we're going to do now is we're going to go back to X-ray. So I'm naming this data set something different just to keep, you can name it whatever you want. I'm just naming it different just to help us stay organized. But we're going to use the exact same function, the XR open data set. The only difference is now we have this argument where we're designating the group. Okay, so we're saying group equals, and it has to be, the exact name, the correct spelling, and that space in between. Okay. And then we're going to look at the metadata. Okay, so if we run that, so now you see it looks a little bit different, right? So now where before the data variables, it said 0, now we see there's 25. And if you click on that little arrow, it will show you all the names of the data variables, the 25 data variables in the file. Okay. Another thing, before we look at those in detail, I want to point out where it says dimensions. The dimensions, these are one-dimensional data arrays. Okay. And they have the dimensions of N fire. That stands for the number of fires. So that's literally the number of fires that VIIRS sensed in this particular granule. Okay. This file. So in this file, there are 636 fires that were sensed. Okay. So this number of fires will change for each VIIRS file that you look at. So if we open, so this is the first one we open. If we open the next one, it's going to have a different, this number will be different. Okay. Okay. So now if you go under the data variables, just like we did last week, any of the variables that you're interested in, if you click on the icon that looks a little bit like a file, it's the attributes icon. It will open up and it will show you the metadata for the particular variable. So there's not that much in these files. It just has the longer name. In this case, it's the latitude of the fire pixel. And then we can look at, again, the FP longitude. That's the longitude of the fire pixel. So this FP latitude and FP longitude, those are the two variables that we're going to need to plot the fire detections. So the locations of the fires. Okay. And then we're also going to need this one, FP power, FP underscore power. FP stands for fire pixel. That's what FP stands for. Okay. So this is the fire rated of power variable. And we can see it has units of megawatts. Okay, and if you remember from last week, if you click on this, this little cylinder icon, this is the data repository. Often, if you click on that, it will give you like a little snippet of the data array. But in this case, at least on my computer, it's just telling me how many values. It's not showing me an example of what the actual data look like. Okay, so in the next step, we're going to actually print out some data so we can see what it looks like. All right, just want to make sure. So does this make sense? So the first thing you want to do is you want to open up, in this case, the group, the Fire Pixel group, and you just want to take a look at, make sure you understand the, the type of arrays you have. So in this case, they're all one-dimensional arrays. Make sure you identify which actual data variables that you're going to need to work with. In this case, it's FP, latitude, longitude, and power. Okay, you can see there's a whole bunch of other ones there too, but we're not going to work with those. Okay, all right. So let's now, we did this last week with the gridded aerosol optical depth beta, but again, I like to actually see, what the data values look like. So we can use this xarray command. It's the xarray data array dot values function, and that will open up the data array as a NumPy array. Okay, so if we run that, so we'll do the latitude first. It'll actually, in some cases, if it's a small enough data array, it'll print out all the values, which is what it's doing here. Sometimes, like we saw last week with the gridded aerosol optical depth data array, it's really large, so it just printed out the beginning and end of the data array. But here we can see, so these are all of the latitude values where the fires were detected. Okay, you can see in this case, there's, it's 600, how many was it? 636 locations, okay, latitudes. And then if we do the same thing now with the FP longitude dot values, okay, we'll see the 636 longitude locations where the fires were sensed, okay? Okay. All right, so now we've come to our first exercise. So now I want everybody to view the FP power data array as a NumPy array. Okay, so we just looked at the FP latitude and the FP longitude data arrays as NumPy arrays. So I want you guys to do the same thing. So in this empty cell here, type in the code and then run it to view the FP power data array as a NumPy array. Okay, and I'll give everybody a second to, or a minute or so to do that. If anybody has any questions, let me know. Okay, did everybody get a chance to do that? Oh, good. Okay. So again, all we want to do is we can just, copy and paste one of these previous commands that we did, and then just change the name of the variable. So instead of FP longitude, we're going to make it FP power. And I can run that. And there now we can see all of the 636 fire locations, what the fire radiative power value was for each of them. Okay, so what data type is this? Does anybody know what this data type is called? Where you have decimals like this? Well, so Julio, that's the units. Yeah, so the units are megawatts. So that's important. Yeah, that's the answer to this question, megawatts. And we're gonna want to know what the units are when we actually plot the data. So I see, yeah, Ludwig and Julio, yes, they're floating point numbers, exactly. So that's good. We see that they're floating point numbers. And if we go back up to the metadata, if I can scroll back up there, go back up to the metadata, so we can see the metadata is saying that they're 32-bit floating point numbers. And so here's our data type, float 32. So that's good. The metadata says they're floating point numbers, and when we take a look at them, they actually are appearing as floating point numbers. So that's good. And then the long name, we already talked about this. They're fire radiative power data. Okay, so just make sure before you go on, again, when you're working with a new data set, that you check all these things. You check and make sure the data type of the data you're actually seeing and printing out in the data array matches what the metadata tells you it's supposed to be, that you know what the actual name of the variables are, and then what their units are. Okay. All right, does anybody have any questions about that? Okay, great. Okay, so another nice thing that we can do before we move on is we can make just a quick plot of the data using X-ray. So if you remember last week, we did the same thing. We made a quick plot of the AOD, the gridded AOD data using X-ray. So X-ray has a lot of built-in plotting functions. So the plots, they're not formatted. They don't look fancy, but they can give you an idea of what the data look like before you move on. Okay, so let's make a quick scatter plot. We run this code. We can make a quick scatter plot. So again, we're taking the DS Spire pixels, we're making a scatter plot, and we're plotting the longitude and the latitude. Okay, and then here C stands for color, so I just made them red colored, and then the marker type. If we go back up here, you can see, so we used this last week. So remember Matplotlib, if you click on this built-in colors right here, this link, it'll open up a new tab. I'm going to close up the NetCDF4. And if you scroll down, you can see all of the different, so these are the basic colors here. There's some other colors, and then like all the really detailed colors are down here. Okay, so any of those colors, you can see the name and you can use that color. And then there's all different marker choices. So these are all the marker choices. And so on the left has the code, like what you're going to type in the Python code. And then it'll show you the actual marker symbol, and then, just in English, what the description is. So I used S, which is the square right down here. So I used a lowercase s, and that makes the square marker. Okay, but you can see all these different choices. There's many choices. So you can pick the marker that you like, and then the color that you like. Okay, so that's actually the next exercise. So I want you guys to actually, in this blank cell, make this same plot that we just did here, except instead of, change the color. So pick your favorite color instead of red, and change the marker type. So instead of filled squares, pick one of the other marker types, and take that and type it in this empty cell, and make this same plot, but using the color that you want, and then the type of marker that you want. Okay, I'll give people a chance. And maybe do a couple different options. See what the different colors or different marker styles look like. So I liked magenta diamond markers. That's what I picked. So you see, I just changed the color, and then I changed the marker style to be diamonds instead of squares. Okay, did everybody get a chance? Everybody see how that works? So even though in the rest of the tutorial, we're going to use red square markers, you have the power to, you know, change the color and the style of the marker to whatever you would like. Okay. You saw in the list of the marker types, there's many different types of markers, and there's many different colors that you can pick. Just make sure when you pick a color and a marker, it's something that's easy to read. So you want, you know, because we're going to be making, you know, these nice plots on maps. You just want to make sure when someone's reading that plot that the markers stand out clearly so that you can see the fire locations and interpret them clearly. So you wouldn't want to pick like a yellow, for example, color, because that's hard for most people to see. Okay. All right, great. Any questions? Everybody looks like they did that. Okay. All right, so now so that was the fire detection. So that's the latitude and longitude of the fires, the locations of the fires. So let's, still using X-ray, let's make a quick plot of the fire radiative power. So you'll see this is the plotting command. So you'll see it looks very similar. So we still have the FP longitude and the FP latitude, but we have this new argument that's called hue, H-U-E. And so that's what we're going to assign as the FP power variable. And again, we still have a marker. So again, I'm still using this filled square markers. But now we have an argument called CMAP, which stands for color map. We used the color map last week as well with the AOD data. And so remember, matplotlib, it's this link here. I'm just going to click on it just to remind everybody. So if you scroll down, you'll see you want to make sure you pick a sequential color map. You have all the different choices of color maps. Okay, and if you keep going, there's more. And then if you skip past the diverging and down to the miscellaneous, there's even a few more of the sequential color maps. So there's a lot of choices. Okay. So I like, for fire rated power, I like autumn reverse. Let's go back. Let's find autumn. All right, here's autumn right here. Whoops, I guess I can't highlight it. This is autumn. And remember, if you reverse a color map, so in this case, instead of going from like red to yellow, it'll go from yellow to red. Okay. And the way you reverse a color map is you add _R to the name. So autumn _R is reversing the autumn color map. Okay. So you have all those color maps that you saw, and then you have twice as many because you can reverse any of them. All right. So if we run this, we'll see we get something that looks very similar to what we saw with the fire detections. The difference is now is that instead of just the locations of the fires, we have them shaded using this color map to indicate the fire radiative power in megawatts. Okay. So again, this is nice. This isn't something, we would ever, use, in a report or in a homework, but we, or a presentation. But if you're just exploring a new data set, it can be really helpful to just make these quick plots to see, the full range of the data and, their locations in terms of latitude and longitude. Okay, anybody have any questions? Okay, great. Oh, and I should just mention again, remember, you can always pick whatever color map you want. I'm just using, I just like this one, but, you can feel free, obviously, to pick whatever color map that you like. The only advice I give you is just make sure it's something that it's, easy to interpret. Okay, so now we're done with that data set, the fire pixels. So we're going to close that up before we move on. Okay, so let's just close that. All right, and so I want to mention, so again, let me scroll back up for a second. Let me go back up to where we opened the file using the netcdf4 package, and we found those group names. Remember, we did this back up here. Okay, so we just looked at the fire pixels group. There's also this other group called fire mask. Okay, so I just wanted to mention that before we move on. So I'm going to scroll back down to where we just were. Okay, So I'm back at this section where it says process fire pixel data arrays using the fire mask. Okay, so the fire mask group, it has a data variable in it called fire mask underscore fire mask. Okay, and what that does is it classifies each pixel in the VIIRS file into one of 10 categories. All right, and so because not every pixel is a fire, but the ones that are fires, they are designated either as an unclassified fire, a low confidence fire, a nominal confidence fire, or a high confidence fire. Okay, so these confidence flags, if your application requires it, you can filter the fire pixels using these flags. So for example, let's say you only wanted the high confidence fires. You would use the fire mask variable in the fire mask group to do that filtering. All right, we're not going to do that today because the fire team recommends using all confidence. So we don't really need to for this application, but maybe you were doing something like modeling or something else where you only wanted the high confidence or just the high and nominal confidence. Okay, I just want you to be aware that the fire mask group is where the variables are that you use to do that processing. Okay, so let's actually, so in the next exercise, I want you guys actually to open the fire mask group and read the metadata so you can see the fire mask variable. Okay, so in this block here, I want you to, I took the liberty of naming the data arrays because I didn't want people to get confused. But type in the rest of the code to actually open the fire mask group and then show the metadata. Okay, so I'll give people a chance to do that. And the answer is below if you get stuck, but try to figure it out on your own before looking at the answer. So again, it helps if you go back up to where we opened the fire pixels group. You can just copy and paste that code and then just change it. Change the name of the group. So I'm just going to copy that. Just make sure you change the name of the group. Okay, and so we're going to change this to fire mask. Okay, and this is fire mask if I can't type. Okay, so you see this is exactly the same as we used before. The only difference is we're changing the name of the group. So they were opening the fire mask group instead of the fire pixels group. Okay. All right, so if we do that, we can see now this group looks different from the fire pixels group. So the first thing that we notice is that the dimensions are different. So the variables in this group have two dimensions. They have dimensions of row by column. Okay. And then also there's different variables. So there's only 3 data variables in this group. So there's the fire mask, which is the one I mentioned, and there's 2 other ones we're not going to talk about. So again, with the fire mask, if we click on the attributes, we'll see that this is the fire mask variable that I was mentioning. And you can see there's here's the 10 different classifications for each pixel in the file. So they're integers from 0 to 9, and then you can see the meanings of each integer. Okay. So there's something called a bow tie effect. We're going to talk about that in a second. Okay, a bow tie pixel. And then you can see there could be sun glint. Okay, so that's when there's a reflection on the surface of water. Usually it's the ocean or a large lake. And it's a reflection of sunlight at the same angle that the sensor, VIIRS in this case, is looking at the surface. So when you have glint, it's very reflective. So usually you don't get any level 2 fires or aerosol observations in a glint region. So then there could be an area of water, clouds, clear land, and then the fire pixels. So as I mentioned, the unclassified, the low confidence, the nominal confidence, and the high confidence. Okay. All right. So did everybody see how that works? Okay, and so actually, I'm gonna add. I want you to see the values here. I'm just gonna add. So if you hover in between any of the blocks, either two text blocks or a text and a code block, you'll see these little icons come up. So I'm just gonna add a code block, okay? And I actually I want you to see the fire mask variable as a NumPy array. Okay, so it's desc fire mask. I just want you to see some of the values. Dot fire mask values. So I'm just opening this array as a NumPy array, just like we did for the fire pixels group. So I just want you to see it. So so you can see again in this array the values. This is just the beginning and the end of the array. Okay, so you can see at the beginning of the array, the fire mask is corresponding to 1, and so 1 is a bow tie. Again, I'm going to talk to you in a second about what a bow tie means. And at the end, it's 0, which is not processed. Okay, so again, that's how the mask works. So for each pixel in the file, it's going to have one of these 10 integers, and the integers correspond to these different flags. Okay. All right. Does that make sense, everybody? Anybody have any question about that before we move on? So the reason we're not processing is because the fire team recommends using low, nominal, and high confidence. So we're just gonna, we're gonna plot all of them. Okay. All right, so let's, again, every time you open a data set or a file, we want to close it when we're done with it. So let's close that fire mask data array before we move on. Okay. All right, so what we're going to do next is we actually want to plot the data from all of the files we downloaded, right? So remember here, we actually have these 10 VIIRS fire files, and we want to plot the data from all of them on a map, okay? So there's kind of 2 different ways you can do that. The fire files, the way that they're set up, you can actually use this very handy function in Xarray called MF dataset. So that will allow us to open all 10 of these files at one time, okay, instead of opening each one individually and plotting it. We can open them all at once into one big data set, and then we can just plot all that data from the data set on one map. Okay, so in order to do that, the first thing we have to do is we have to grab all 10 of these files. Okay, and so I'm just defining a variable for that group of files called file list. Again, you could name this whatever you wanted. And we're using this syntax here. Okay, this is the pathlib module. Glob means just grab all the files. Okay, and then in parentheses with this little star, this is a wildcard. So this is saying grab all of the files that start with AF-IBAND, okay, that are in the VIIRS path that we named. So again, the VIIRS path is the directory path that corresponds to this VIIRS files directory on the Colab instance, okay? And then if you're not sure, so this is actually grabbing all those files. We can print out the files and just check and make sure we got them all. So this is optional, but I just thought it might be nice. You might like to see how we grabbed all the files, okay? So now we've got all our 10 files. And so now we can come down and we're going to make a new data set. I'm just calling it multi for multiples. And we're going to use, instead of XR open data set, we're using XRMF data set, okay? And so we're going to open the file list, which is where all our files are. This is the same. We're using that same engine, the netcdf4 package. But here, concat-dim, this is the dimension that we're concatenating along, okay? And it's n-fire, the number of fires, okay? So this function, we can only do it if the data file has a concatenating dimension, okay? So when we get to the aerosol optical depth files, we can't actually use this, unfortunately, because there's no concatenating dimension in the AOD files. It'll only work for the fires, okay? And then again, we have to specify our group, okay? So if we run this, we'll see now we have a new data set, and you'll see NFIRE, the number of dimensions. So remember when we opened the one file before, it had 636 NFIRE dimensions, so there are 636 fires in it. So now you can see this one has almost 6,000 fires, and that's because it's the sum of the fires from each of those 10 individual files. Okay, we open them all up into one data set. And you see, if you look at the data variables, they're all the same data variables as before. They're just this Dask package basically gathers them together. Okay, does that make sense? Hopefully. I don't see any questions. Okay, great. So that's just a convenience. Okay, this is just a convenience. So this is, again, is just instead of making a loop where we loop through each of the 10 files and open them one at a time, we can open them all at once into one data set. Okay, and that's what we just did here. Okay, so now that we have all of our files open, let's actually plot the data. So let's make those two plots I showed you. So the first one is the fire detections plot. And so again, we're plotting on that Esri world map topographic background that we made last week. Okay, so this is, just has more information about the plotting functions. But let me show you. So you remember this from last week, hopefully. This is where we're using the CartoPy package interface, and we're actually going to link to the Esri world topographic map tiles and then set that up using CartoPy. So let's run this. We won't see any output yet. And then in the next block here, most of this code should look very similar to last week. Okay, so if you remember, we had to set a zoom level. That was, let me pull this back out. So that's the zooming in, the scale for the region of the map tiles. So remember, we use zoom 1 for the global map. And so if zoom 6, this is zoom 6, this is zooming us in, I think, just about perfectly to see this particular region. Okay, so that's what this 6 is. And then here I just set up some variables to set the size, the color, and the type of markers. Okay, so again, when we're done, you can feel free to change this. So again, I'm using red markers that are filled squares, but you could change these if you wanted to have a different type of marker. I suggest keeping the marker size 2 because you don't want to have markers that are too big or too small. But you can obviously on your own, you can play around with that and change the size of the markers and see how that makes the plot look. Okay, but two's a pretty good place to start. Okay, and then all of this is going to look the same as last week. So we're setting up our figure. We're setting up our figure. Okay, we're using a map projection, which is the same map projection as the map tiles background. Okay, we do that for the best results. Here we're actually adding the map tiles background and the attribution, which is that little text box at the bottom. Let's see if I think I can zoom in here. The little text box at the bottom that basically just gives the attribution to Esri and the creator of the map tiles background. Okay, whoops, I want to zoom in too much. Okay, and this is where we zoom into that geographic region. Okay, we don't want the global map, we're zooming into Western Central South America. Okay, here's the actual plotting function right here where we're plotting the data. So we're using the matplotlib pyplot function. And so we're plotting the longitude, the fire pixel latitude, and we set the marker color, the marker type, L width equals 0. That's saying line width equals 0. Okay, you need to keep that there. The marker size, and then remember from last week, we always have to have this argument, this transform equals CCRS plate carré, because that's telling the CartoPy package that our fire data are in latitude, longitude coordinates, geographic coordinates. Okay, so that always has to be there, no matter what your map projection is. And here, this is where we did this last week too, where we're pulling out information from the file name, the satellite data file name. And we're reformatting it to make the title for our plot here. In this case, it's going to have the satellite name, VIIRS, the product, in this case, it's fire detections, and then the date of the observation in a nice format that's easy to read. Okay. So I think most of this is review from last week. The one thing that's new here is that I used a dictionary to pull out the abbreviation of the satellite name. Here. So it's this, in this case, it's this J01 right here. And you can see that I've assigned for J01, I've assigned that as NOAA 20. So the reason for the dictionary is just it allows us to reuse the same code for any of the satellite files. So if we had a SNPP file or a NOAA 21 file, this same code would work. So it just makes it a little bit more universal. Okay, I thought it would be helpful for you. And then we did this last week. We pull out the abbreviation, the 8-digit date, and we reformat it. Okay, and then we make the title, we add the title, we show the plot, and then we save the actual map image file, the PNG file, we're going to save it to this map plots directory. Okay, so if we run that, okay, should be pretty quick. And then refresh. There it is. So there's our PNG file, which has our fire detections. Okay, did everybody get that to work? Does anybody have any questions about? So again, most of the code should be a review. The main new points are the actual plotting function right here. That's new. And then the dictionary, that is also new. But everything else should be a review from last week, or yeah, just last week. Okay. Does anybody have any questions? Problems? Okay. I don't see anything.
¿Todo el mundo ha llegado a poder obtener este mapa? ¿O necesitan más tiempo para llegar a donde estamos?
Okay, I see thumbs up.
Yeah.
Está bien. Okay. Okay, and remember, everybody, pull this out again. So you can mount your Google Drive, and that I think will automatically make copies of all the files that either you downloaded or these map image files. I can't. NOAA security won't let me do that, so I can't demonstrate that for you. The other thing you can do is if you click next to one of the files, there's these 3 little dots. If you click on that, it'll give you some different options. So one of them is download, so then you can download directly. And then I'll show you at the very end, there's some Python code if you'd rather download the files that way. But just be aware that if you want to save any of these, these map files, you need to make sure you download them, because remember, once we close out the Google Colab and then we come back next week, it resets. So all of the files that you made will be lost. Okay. All right, it looks like there aren't any questions. Is that right, Anna? Looks like everybody's good. Okay. All right, so let's plot the fire radiative power. Okay. So in this next section, it's almost exactly the same, okay, as plotting the fire detections. There's just a few differences, so let me highlight those for you, okay? So this is the same. We're setting the same zoom level of 6. Here we're going to, the marker size and type, that's the same. But remember, for the fire rated of power, we need a color map, okay? And again, I'm using autumn reversed. You can, of course, use whatever color map you'd like. And then I'm picking a color for the data that are greater, that were plotted that are greater than the maximum, which in this case is 1,000. I'm setting the maximum limit as 1,000 megawatts. Okay, so anything that's greater than 1,000 megawatts is going to plot as this maroon color. All right, remember we did this last week when we plotted the aerosol optical depth gridded data. Okay, and so then this is the same. Okay, this is all the same here. We're setting up our figure. We're setting the map projection. We're adding the attribution. We're changing the geographic domain to zoom in to the Central, Western, South America region. Here, this is where we're setting the color map. Okay, so we're using matplotlib to get the color map we specified up at the top, and then we're plotting any of the color or any of the data that are over that maximum of 1,000 megawatts. We're plotting it that specific color. Okay, here's the plotting function. So now we're using the matplotlib scatter plot function. Okay, so again, we're plotting the longitude, the latitude, and then C stands for color. Okay, and so that's where we're plotting the fire rated of power data. And we're following, there's a convention when working with fire rated of power data to plot the log 10 of the fire rated of power. And the reason why is because there's a fairly wide dynamic range for fire rated of power data. It can have values all the way from close to 0 to over 1,000 megawatts. So typically the log 10 of the data is plotted just to be able to show that dynamic range on a single plot more clearly. Okay, so that's why we're using the NumPy package to take the log 10 of the fire rated of power. Okay, and then we have the marker type and the marker size. You notice the marker size, we're squaring that. And I have a link. The reason why we do that is, I think I have the link. Yeah, right up here. It's just because the scatter plotting function sets the size of markers differently than just the plain plot function, which we use for the fire detections. So we're going to end up with markers that look the same size. Okay, but we have to use this syntax for markers in the scatter plotting function. Okay, so if you're wondering what that is. Then we have the color map we selected. And again, this is where we're setting the minimum for the plotted data and the maximum for the plotted data. Okay, and again, the plotted data are FRP log 10. So we're going to basically be going from 0 to 1,000 megawatts on our plot. And we saw this before. Again, we always have to have this argument, the transform equals CCRS plate carré, because the data we're plotting are in geographic coordinates. All right. Then we're adding a color bar. Okay. And then everything else is the same. So let's plot those data. Okay. Okay. So again, you'll see we have the different colors and we have our color bar at the bottom. So again, the actual data are plotted with the log 10 of the FRP. So the way we can display the color bar is still in megawatts. So you could change these units to the log 10 of megawatts, but I feel like this is a little bit more clear to have it this way, like when you're interpreting the plots. All right, and then you should see this out here. You should see the fire rated of power PNG file under your map plots. Okay. And it looks like there's a question from Christian. Could you translate that, please? Something about a question about the Amazon.
Okay. A question about the Amazon, is it normal that there are no Marcadores, I assume it means no allocations, no fire radiated power areas. Maybe we can extend. It looks like he put the coordinates in there that he used. Pero sí vemos, ¿no? En el Amazonas algunas zonas del el fire radiated power. ¿Se refiere a que no ves, Cristian, te refieres a que no ves los puntos en el Amazonas, en la zona del Amazonas? Ah, te refieres a la parte norte, en la parte norte del país, ¿no? Yeah. Yeah. Yes. See. Yeah. Okay. So in the northern part of Bolivia, there's no data indicated. There's fire radiated power.
What,
Right. Yes,
right
that area
here?
there.
Yeah.
Yes. Yes.
Okay.
Yeah.
Well, that could be just for this particular day. I mean, again, we're just looking at one day, one satellite, at a specific time of day. This is the early afternoon local time.
Sí. O sea, que es posible que es por ser, solo estamos mirando un día específico. Entonces, quizás mirar otros días y a ver si varía. Are there false, Christian, que espero que contestáramos tu
Are there
pregunta.
false detections? So it's possible. VIIRS is very accurate, so there should be relatively few false detections for VIIRS. Whereas when we do ABI next week, there's much more likelihood for false detections with the ABI data. But the VIIRS data are quite accurate. So it's certainly possible that there's false detections, but it should be less likely. And so Oran asks, how can I get the FRP values for any particular latitude and longitude? I don't think I understand exactly what you're asking. Do you want to?
Probably for a pixel that containing a particular latitude and longitude, right? Extract the pixel at a particular location and then, right, that's what they mean. That's
Okay.
what that means.
Yeah, so there's a technique. Typically what people will do is they will pick their point, their latitude and longitude, and then they in Python will essentially draw a circle around that point with a radius of 27.5 kilometers and match up the VIIRS observations anywhere in that circle and basically count that as being that particular latitude longitude location. So I don't have the code to do that, but you could I'm trying to think who has that. I feel like Powan, like one of the RSET trainings has that, Anna. We could search.
Okay, yes, we can check. Podemos mirar.
I know Powan's covered that topic.
Yeah, I mean,
that's
how
what a lot of people are interested in.
Do you ever look at, for a particular lat long, say like a city or a location, extracting just the pixel at that value? Do you have code for that or
well, again, that's what I'm saying. That's what Powan did. So
Okay.
if you have an ABI file, the grid doesn't change, so it's a little bit easier. But every overpass of the polar orbiting data, the locations of the pixels are different. So that's why, again, this technique that I described, where you take your point, like your city, let's say your latitude and longitude, and you draw a circle around that with a radius of 27.5 kilometers, and you say any pixels that fall within that circle, they are counted as being at that latitude and longitude. So that's the technique.
Yeah, thanks, Amy. That makes sense. We'll look to see if we have a training
Yeah, I'm
already
about
addressed?
95% sure that Powen has addressed that.
Okay.
Yeah. Yeah, because it's a little bit complicated. You can't just it's not like a one-liner. You have to write some code for it. Okay, there's another question.
Okay,
Anna, could
see,
you translate that, please?
yes, if I wanted to download the data from VIIRS AF for a range of dates, for
Yep.
example, from the 1st to the 15th of 11/23, how would I change the code to do that?
Okay, that's a good question. So what I would suggest, I'm going to scroll back up, everybody, to where we downloaded, we searched for and downloaded the data. Okay. So what you would have to do is, how do you say his name? Anna Eldemar? Eldemar? Is that how you pronounce his name? So you would have to set up a loop. This is what I would suggest, because what you need to do is you need to remember this function. Remember this function that I wrote where we're finding the times when for a given satellite and for a given date, and then for your given geographic domain, that the satellite is moving into and out of that geographic region. Okay, and we use these times to subset the set of global files from the cloud archive, the NOD. You would need to set a loop where you would, for each of those days, those 15 days, okay? So the satellite name is going to be the same. The geographic range is going to be the same, but you're going to want to change for each day. You're going to want to change the observation date here, and make for each day, run this code and download the files that correspond to that date. Okay, so that's how you would have to change it. You would have to set up a loop where you would loop through, like you would make a list where you have your however many days, I guess your 15 days, the dates in that list, and then you would loop through that list and run this this function and then the download code for each of those days. Okay. Yeah, that's a good question. That would be a good exercise for you to do.
Yeah, it could even be a project exercise if somebody wanted to,
Yeah.
look at a
Yep.
range of dates and maybe show a loop of a
Yep.
series of images.
Yep. Yep. That's a great question. Okay.
So I'm wondering if this is a good time to take a break. It's almost 5:30.
Yes, we're going. I just want to make sure. I had that same thought, Anna. I just want to make sure because we're basically at the end of the VIIRS, so I just want to make sure nobody else has any question about VIIRS, the active VIIRS IBAN files, because the next thing is we're going to go on to aerosol optical depth. So, does anybody have any more questions? Those are great questions. But I mean, isn't this pretty cool? I know a lot of you use GIS, so you may not want these images. You can just, extract the individual data themselves and open them in your GIS program. But I don't know, I think it's pretty cool that we can relatively easily get these data and then, plot them on a map. Okay. All right, I don't see any other questions. So let's, this very last code block here, before we go to section 2, let's close that that data array, that data set, that we opened. Okay, so everybody see that? So make sure you run this. Should be right underneath your plot of fire radiative power. Okay, just make sure you run that. And then the next section is going to be section 2, the aerosol optical depth. I strongly recommend that every time you're working with a new satellite data product, that you take one of the files, that you open it up, and that you make sure you find all the data variables, and you check the valid range, the units, the data types. So now the difference with the aerosol optical depth files is this time we do need to process the data. So again, if you remember from week 1 and then last week, the aerosol optical depth data have what are called quality flags. So there's high, medium, and low quality. Okay, And so the science team recommends that for quantitative applications, you use high quality AOD only. And for qualitative applications, you use high and medium quality data, okay? So what we're going to need to do is we're going to need to find the QC all variable, okay? And we're going to set it equal to 0 for high quality AOD, and we're going to set it to less than equal to 1 for high and medium quality AOD, okay? And the reason I know this is because I read the VIIRS AOD user's guide, okay? So again, you always want to make sure you read the documentation for the products before you start working with them, because that's where you're going to get the information about the proper quality flags and screening to do, okay? All right, so this is the same process that we used for the VIIRS files. So the first thing we're going to do is we're just going to set the directory path to one of the files, the first file that we downloaded. Let's run that. And then we're going to use the XR open data set to open that file. So again, this is exactly the same as what we did before with the VIIRS files. Now the difference, you'll see some differences immediately. First of all, this file, the VIIRS AOD files, do not have groups, okay? So when we open the file, we can see immediately, we can see the attributes. That's the global metadata for the file. So again, you can see it looks similar. It'll, have information like the processing level to level 2 file, the actual spectral bands of VIIRS that were used for AOD, that it's a NOAA 20 VIIRS file, information about the times and the dates of the coverage, and then the latitude and longitude corners. So all sorts of just general information, okay? This particular file, so there's 1, 2, 3, 4 different dimensions that the variables can have. We'll see under coordinates here, we'll see the latitude and longitude. So again, if we click on the attributes icon, we can see more information about each of the variables. So we can see that latitude is in degrees north. We can see the valid range, okay? If we click on the data repository button, again, sometimes we can get a little snippet of the array, but this one's way too big. So we just see how many values, and we know that it's a floating point numbers. Okay, same thing with longitude. It's in degrees east. You can see the valid range. And again, they're floating point numbers. Okay. Okay. So I'm just gonna, let me hide all that. Okay. So now we know if we open up the data variables, there's 28 data variables in this file. Again, we can see them directly because there are no groups in this file. So if we scroll down, we can take a look at all the different, there's a lot of information in this file. All right, so we know we want to find the QC all variable. That's our quality flag. So again, if we click on that, we can see, again, it's the AOD retrieval quality. And so there's the valid range. And then the other variable that we want is AOD 550. So again, if we click on that, we can see this is the aerosol optical, AOT is aerosol optical thickness. That's a synonym for aerosol optical depth. And it's at 0.55 microns or 550 nanometers for over ocean and land. So we can see the valid range. So if you remember from the slides, which we had last week, the valid range for AOD, for VIIRS and ABI AOD is minus 0.05 to 5, okay? And units equal 1, that just means there's no unit. So AOD is unitless. It doesn't have any units, okay? All right, anybody questions about looking at the metadata, opening the file and looking at the metadata? Okay, so you can see there's a lot of other variables in the file that we're not, that aren't relevant for us. We're not going to look at any of those. Okay, great. So again, like I said, I like to see like an actual example of what the values look like. So we're going to use the X-array data array values function again to open up. Let's open up the AOD 550 data array as a NumPy array. So now we can see a little bit of the beginning and the end of the data array. So we can see that most of the pixels at the beginning and the end are actually masked, so there's no AOD retrievals. But we can see there's 3 retrievals here kind of at the end of the beginning, where we can see that there are AOD values and they're floating point numbers. Okay, so again, the data type is a floating point number. Okay, so let's do the same thing for the QCall data array. Okay, and we can see, makes sense, right? So any of the values that are masked that have the NaN, that's corresponding to a QCL equality flag of 3. And if you remember from the metadata, 3 means not retrieved, so that makes sense. And then the 3 values where we can see, see the actual values of AOD, those correspond to the QCL value of 0, which is high quality AOD. Okay, so that makes sense. So hopefully you can see how for each of the AOD values, they have a corresponding QCL flag value that's going to indicate whether the data was not retrieved, whether it was low quality, medium quality, or high quality AOD. Okay, and so when it gets time to plot the data, we're going to use the QCL variable to filter the AOD, and we just want to plot. So we're going to start by plotting just the high and medium quality data, and then I'm going to give you a chance to plot just the high quality and then all qualities, high plus medium plus low, and we can see what the difference is. Okay. All right, and then let's see, I wanted to actually print, I think we did this last week as well, look at the data range of the values in the array. So again, we can use the NumPy package to give us the NaN min and the NaN max. And so we can see, so the minimum of the values, it actually corresponds to the range of data in the metadata. So we have data in this particular array going all the way down to minus 0.05 and up to 5. Okay, and remember these small negative AOD values, they don't have a physical meaning, but they correspond to the uncertainty in the AOD retrieval. So essentially the calculations from the AOD algorithm. And so we're going to think about these very small negative values. We're going to think about them as being very small positive AOD values. Okay, that's how you can think about them. Okay, so we're going to close the data set now that we opened with X-array because we're done with it. And so next we can make a quick plot, again, using the same built-in X-array plotting functions. And when we do that, and so this is exactly the same code we used last week with the gridded data, but we do that, you're going to see the plot looks very strange. Okay, so this really doesn't look like we might expect it to look. And the reason why is, again, this is not a formatted plot. This is just X-array's built-in plotting functions. So it's plotting the AOD data, but it's not georeferenced. So it's, if we scroll back up to the metadata for the entire file. So if you remember the dimensions, let me close the data variable. The dimensions are actually these rows and columns. They're not latitude and longitude. And if we look at the AOD data, where's AOD data? We can see the dimensions of the AOD data are rows and columns. Okay, so when X-array does that quick plot, it's plotting the AOD data with rows and columns, not latitude and longitude. So that's why just the plot itself looks kind of, funny. And then we also have these white these stripes that correspond to missing data. You guys see these stripes both on the right side and the left side of the plot. So what these are, I put the link up here. These are called bow tie, or these stripes, they're caused by what are called bow tie deletions. And what that is, that's a pixel aggregation technique that controls the growth of the pixels, the VIIRS pixels at the edge of the VIIRS scan. So remember the spatial resolution is highest in the center of the scan. So in this case, it's 750 meters at the edge of the scan, or excuse me, at the center of the scan. And at the edge, the the special resolution is going to get slightly larger or coarser. But this bow tie deletion technique, it actually minimizes how much larger the pixels are going to get. So that's kind of the whole point behind it. And if you follow this link, you can read more and see an illustration of how the bow tie deletions work. But I just wanted you guys to see just example of this in case you ever made a quick plot and you're kind of wondering what this looks like. So when we go ahead and plot AOD, we're going to use latitude and longitude. And when you do that, the bow tie deletions, they disappear. Okay, you just see them when you plot the full scan, the full file using the rows and columns. Okay. All right, but at least with this quick plot, we can see, there are AOD data. We know from looking at the file that we have data that go, basically are 0 all the way up to 5. And we're seeing that. So we're seeing, a lot of low values, and then we're seeing a few values of high AOD. So at least this plot, even though it's not geo-referenced, it kind of corresponds to what we'd expect from looking at the values in the data array. Okay. All right. The next thing we have to do is we need to talk about the plotting function for AOD. So if you remember last week, we used the matplotlib p-color mesh function for plotting the AOD data. And this is the best option. It essentially causes the least interpolation of the data. But the problem is that p-color mesh doesn't allow its X or Y argument arrays, which in this case are latitude and longitude. It doesn't let latitude and longitude be masked arrays, meaning there can't be any missing or invalid latitude and longitude pixels. But that's a problem because we already saw with VIIRS, we saw there are some areas where we have these bow tie deletions where there are missing pixels in the VIIRS plot. So there's areas of the file where there's missing latitude and longitude. So we can't use the p-color mesh function, unfortunately. So what we're going to use instead is we're going to use the contour F, which is the filled contours function. So it'll end up looking the same. Like you saw the plot that I made. So it ends up basically looking the same. It's just the actual way that the data are plotted is slightly different. Okay. So one of the things that we have to do is when we're using this contour F function is we actually have to define a data array that has the intervals that we're going to use to plot the data with the filled contours. Okay. And so we're going to use this NumPy function called arrange, and you have the link to the documentation here. And so it's essentially saying, what is the range and then the interval of the array that you want to make. Okay, so we're going to plot from 0 to 1 AOD, and we're setting an interval of 0.05 AOD. So let's make that, and then we can print it out, and you can just see what the contour levels are. Okay, so this is the new array that we made, and so you can see it has these values in it. So it goes from 0 to 1. And each interval is 0.05 AOD. Okay. So you could make this interval smaller, or you could make it larger. So the smaller you make, the more contours you'll have in your plot. So the higher the plotting resolution will be. The lower the number of array of contours, then kind of the coarser the plotted data will be. Okay, so for AOD 0.05 is a nice balance. So that's why I recommend it. But you could play around with this contour interval if you wanted, and see how that changes the appearance of the plot. Okay, so this is just a setting that we have to do, or we have to set in order to use this contour F function. That's all that is. Okay, so now that we've done that, we're actually going to plot the AOD data. So let's scroll down and we'll see what this plotting function looks like. So again, a lot of it is similar to what we saw with the VIIRS plot, but there are some important differences. So the first thing is at the top, I've defined a variable that I'm calling quality. And this is where we're going to set the AOD data quality that we're going to use to plot the data. Okay, so remember, high quality is what we use for quantitative applications. We recommend what we call the top 2 quality, which is high plus medium for qualitative applications. And we don't ever recommend using low. Okay, so all quality is high plus medium plus low. We're just going to plot it so you can see what it looks like. But the low quality, if you remember from the slides that I showed last week, has a lot of erroneous AOD values. So that's why it's not recommended. Okay, so we're going to start by plotting the top 2 qualities, the high and medium. Then what we're going to do is we actually have to set up a loop to loop through each of the 10 AOD files and plot the data, open each file and then plot the data, and then close the file and move on to the next one. So the first thing we're going to do is we're going to actually grab all those files. So again, we're using the pathlib module. The glob means to grab all the files. And this wildcard means that we're getting all the files that start with JRRAOD and end with .nc. Okay, so that's going to get all of the AOD files from our VIIRS files directory. Okay, then this part is going to be very similar. We're setting up our figure in Matplotlib. We're adding the geo axes with CartoPy. So I picked the plate carré map projection. So you could change this to be a different map projection if you wanted. Okay, just be aware. This is again where we're setting the extent. So we're zooming into the Western Central South America region. Here we're adding the latitude and longitude grid lines and grid labels using the CartoPy package. Here's where we're adding the shading and the coast for the coastlines and the borders lines. Here we're getting the color map. And so I could have defined, a color map variable like we did for the VIIRS plots, but for whatever reason I didn't here. So if you wanted to change the color map, you would just come in here and change this directly. I like the rainbow color map for AOD, and we're going to use dark red to indicate the AOD value is greater than 1. Okay, we used the same combination last week when we plotted the big gridded AOD data. Okay, and so then here's our loop. So for each of the 10 AOD files that we collected, we're going to, for each one, we're going to open up the file, okay, using Xarray. And here we're going to set the data quality using the QCall variable like we saw. So if it's high quality, we're just going to plot the high quality data. If it's top 2, we're going to plot the high and medium quality. And if it's all quality, we're going to plot the high and medium and low quality data. Okay. And then here's our plotting function. So again, like we said, it's the contour F function. So we're plotting the longitude, the latitude, and the AOD data. We're using the where function in Xarray. So where I have the link to it, the documentation up at the top somewhere. Oh, where did I put it? Where? Here it is. Xarray data array where function. So here's the link. So what this does is it actually it selects just the pixels that correspond to whatever's in the where. So in this case, let's go back down. We're setting where the plot quality. So we set the plot quality right up here. So this is, in this case, we're doing top 2. So we're just going to grab the AOD data where the QCall variable is less than or equal to 1. That's going to give us the high quality and medium quality AOD data. Okay. So here we're adding a color bar. Here, this is where we're making the plot title. So this is almost exactly the same as what we used for the active fires. So again, this is automatically making this title here for the top of our plot. So essentially we know what date this corresponds to and the satellite and which satellite it is. And then here we're going to save the figure. Okay, so let's run this. So this will take better part of a minute. And we'll see Once it's done, we'll see the plot, and we'll see the new file saved here in the map plots directory. So this will take a little bit longer. It takes a little bit longer to plot the AOD data than the VIIRS data, just because the files are bigger. Oh, and remember, so we saw this last week. So remember, you'll see these download warnings. And that's because the first time you download the shape files that correspond to setting the the background, the land and ocean and lakes, and then the coastlines and the national borders, those shape files, the first time you download them, you just get this download warning. So you can ignore those warnings. Okay, so now we see our plots. Okay, and we should see, yes, here it is up here. So we've under the map plots, we'll see we have our data file. And I included the data quality in the file name just so that we don't get confused. So we remember that this is the top 2 qualities of AOD data. Okay. All right. Does anybody have any question about that? Does everybody get that plot and get the PNG file to save? And so again, you can see, like I showed before, you can see the difference. This is the plot we just made. And these missing data, these are these gaps here. These are because there's clouds, mostly. There's clouds, okay? Whenever there's clouds, remember there's no AOD retrieved. And then, comparing, this is what we plotted last week. This was the level 3 file that has 0.01 degrees resolution. So you can see the pixel sizes are much larger compared to the level 2 product, which is 750 meter resolution. Okay. All right. Does that work for everybody? Does anybody have any questions? Okay, so.
Entonces, llegaron a conseguir el mapa del AOD. Si nos pueden indicar si llegaron a este punto, y entonces una vez que nos indiquen ya podemos seguir con el próximo,
Okay.
la próxima sección. Yeah, I'm asking everybody if they got to the AOD.
Does somebody, so can you read that from Lionel, Anna?
Yes, how can I do a correlation between ARNet and VIIRS for AOD?
Yes, that's a great question. So that's what, if you remember the slides from last week, that's how AOD, the VIIRS AOD is verified, is using the ARNet. And so that goes back to the question from before the break. So what you need to do is you need to do what are called matchups between the VIIRS AOD and the ARNet AOD. So you have to start by, for the location of the ARNet station, you draw a circle around that location, that latitude, longitude, with a radius of 27.5 kilometers. And you spatially match any of the VIIRS pixels, the VIIRS AOD pixels that fall within that circle. Those are considered to be at the same latitude or longitude location as the ARNet station. Then you have to match temporally the time of the VIIRS observations with the time of the ARNet observations. Okay, so it's actually it's relatively complicated. And yeah, it looks like Odon is asking the same question. So I can't actually give you that code. My supervisor doesn't like us to give out the matchups code. But again, Anna, I'm fairly certain that Pawan covered this topic in an RSET training. So Lionel and Odon, I think that hopefully Anna can go back and find an example of that code that she can share maybe next week.
Yes, I'm sure there's code somewhere at NASA that we can share.
It's actually fairly complicated. It's not just like one line of code. You actually have to do a little bit of work.
Yeah, I mean, we can find NASA code to do this. Of course, it would be getting the AOD files from the NASA archives, right? So one thing we haven't explained yet is that the VIIRS data specifically you can find in several places. Amy's teaching us how to find them through NOAA, through the NOAA archives. They're also available through the NASA archives. The products are slightly different, but we have trainings that we do through NASA that cover how to do that. So I'll share, I'll share that information next week.
Yeah, but the matchups code should be the same, Anna.
Right, the matchups code is it, but it will be retrieving, data files from somewhere else.
Right, but that part of the code doesn't matter. So it's the actual matchup. So it's pulling out the AOD from the VIIRS file and matching it to the AirNet station.
Mm-hmm.
So that part won't be any different. Getting the VIIRS files in the first place might be different, but the part of the code that's doing the matchups, that should be the same.
And reading the files, etc. Yeah.
Yeah, and reading the files should be the same. Yeah. I mean, so the actual variable, the AOD variable name may be slightly different, but I think it would be similar enough that,
Yeah,
Lionel and Odon could figure it out.
Yeah, there will be some differences. So that's why I just wanted to clarify that there's VIIRS data that you can get from different places.
Yeah. Well, the other thing is they'll have to go to the AirNet site and download those data sets as well.
Okay.
So to do the matchups, you have to have the VIIRS AOD files, and then you have to have the AirNet AOD files as well.
Yes, correct. Thanks, Amy.
Yeah. No, those are really good questions. They're just, the answers are not simple. Okay. Any other questions? Okay, so what I would like, I think we have plenty of time, is I would like you guys to, so what we just did here, this is the plot of what's called the top two qualities, the high and medium quality AOD. I would like you to go back here to this code, and I'd like you to modify it, okay, and rerun it first to plot just the high quality AOD. And then when that's done, and so you'll make a new plot, and then it'll save a new file over here in your matplots. And then when that's done, go back and change the code again to plot the all quality, so the high plus medium plus low. Okay, and then when we're done, we'll have 3 plots of AOD, and we can take a look and see what the differences are on the plots. Okay, so everybody please. And if you get stuck, you can ask me for help. But essentially, all you have to do is change one part of the code, one setting, and then rerun that same code block. Just rerun it again, and it'll plot either the high quality or the all qualities data. If you have questions, you can let me know. And I have those plots. And just a warning, it will take longer to plot the all qualities data just because you're plotting a lot more data. So I think that one took, I don't know, a minute or two. So when you get to that one, the all qualities, it'll definitely, don't be alarmed, it'll definitely take longer to plot than, for this block to finish running. It'll take a little bit longer. So like it took 36 seconds. I think maybe it takes closer to a minute and a half or maybe 2 minutes to plot the all qualities data. So just don't be alarmed. Does anybody have any plots yet? Does anybody have any questions?
¿Consiguieron obtener las gráficas después de modificar el código? Si nos pueden indicar, gracias.
It looks like some people have. Okay, that's good. Okay, so for anybody that's having trouble, what you want to do is you want to come back up to the top of the code block where we set the quality variable. And so you just want to change that. We had set it to top 2. We want to set it to high. And this will plot, and then we're going to plot it again. This will plot just the high quality AOD. So we can do that one first. Okay, there it is. Okay, so then if I refresh, so now we can see. So now we have the top 2 that we started with, and then we also have the high quality. And then go back up. Oops, I went too far. Go back up. And then now if we want to plot all qualities data, we change from high to all, and we run again. And that's going to plot, like I said, this one's going to take a little longer. I think it takes close to 2 minutes. And this is going to plot the high, the medium, and the low quality AOD. Okay, so there's the plot. It's going to take a little bit longer to finish saving the file. Okay, that's done. Okay, so again, if we refresh here, we'll see now we've got the all qualities plot. All right, so is everybody able to get those to work? Did anybody have any problems? Okay, so let's take a look. So this is the top 2 qualities. And then let me pull up the high quality. So this is the high quality. This is the top 2 qualities. High quality, top 2 qualities. High quality, top 2 qualities. So what differences do you guys see with the high and then the top 2?
¿Qué diferencias ven? ¿No pueden escribir o hablar si quieren quitar su micrófono por unos segundos? Abrir su micrófono.
What differences do people
¿Cuál
see?
es la diferencia entre las dos imágenes?
Yeah, so Ana Maria says there's more data. Yes, there's more data in the top 2 quality, right? Because remember, the high quality, the screening is very stringent. So this is the high quality. We have less coverage, so there's fewer AOD retrievals, but we have the highest confidence in that. So we're pretty certain that all these pixels actually correspond to aerosols. Okay. Whereas with the top two, which is this, we have more coverage, but we see there's very likely some of these higher AOD, like along the coast, like over where the Andes are, those are probably erroneous. They probably don't actually correspond to aerosols in the atmosphere. They're related to, the reflective surfaces of the mountains. Okay. And then if we look at the all qualities, so here's the all qualities, you can see there's much more. I think somebody mentioned this. Ludwig mentioned this. So there's a lot more coverage when you add in the low quality, but you can see there's even more areas where these dark red, these high AODs along the Andes, and those are definitely erroneous. So, these don't correspond to aerosols in the atmosphere. They're just, erroneous high retrievals from the algorithm. Okay, so that's why we recommend that you don't use the low quality, okay, because you get these high AODs that are erroneous. So they could be confusing if you don't realize, what you're looking at, okay? So don't use the low quality. This is the high quality, or the top two qualities are recommended. Okay. All right, any other comments about the three different, like looking at the data flags, the quality flags? Okay. And if you were doing matchups with AeroNet, we recommend using the high quality AOD only. Okay, so for Odon and Lionel, we're going to do matchups with AeroNet AOD. Typically, again, that's high quality AOD only. VIIRS AOD. Okay. All right, so the very last part, this is just a reminder. I mentioned this before, but I'm going to mention it again. Any of these files, these map files that we generated, the PNG files, if you want to save them, just make sure you save them to your Google Drive, or you download them to your local computer. Okay, and again, you can do it manually. You can click on these little dots next to the file name, and there's an option to download. You can click on that, or this code block here will actually, using the Python code, will download. I just did, for the AOD, I just did the top two, but you could, add some lines and copy, and then just, change the file name to the AOD, or to the high quality, or the top, or the all quality AOD if you want to download those files. Okay, and if you run this, I already downloaded the file, so I'm not going to run it, but if you run this, it will open up a window and it'll let you pick the folder on your local computer that you want to download the files to. All right. Okay, does anybody have any questions about what we covered today? Any questions about Python or about the VIIRS data? All right, and I think you wanted to go over the homework?
Yes, we're going to go over the homework. Voy a repasar la tarea que se mandó, la primera tarea. Muchas gracias por entregarla. Entonces, en esta tarea teníamos la primera pregunta, que era: seleccione el sensor con la mayor resolución espacial para datos de la profundidad óptica de aerosoles. So the first question was: select the sensor with the greatest spatial resolution for aerosol optical depth, GOES 16 or VIIRS. Y entonces, ¿cuál era la pregunta correcta en este caso? En este caso, I actually can't see the chat while I'm sharing. Hopefully people are answering in the chat. What's the correct answer to this? Mm,
No, Anna. Somebody answers. People answer. VIIRS.
right, VIIRS is the correct answer. Amy, do you want to say anything about this? The answer to this question? Amy? I think we've lost you. Amy, are you there? We don't hear you. Ok, so VIIRS es la respuesta correcta en este caso. Efectivamente que tiene 750 metros en lo que es el nadir o el... Amy, you're muted, that's why we're not hearing you.
Sorry. I'm sorry. Did you ask me a question, Anna? I'm sorry.
Yes, you were muted. So no, I was just wondering if you wanted to say anything about this first question, which was the spatial resolution, VIIRS versus ABI, which was the higher, which of the two has the higher spatial resolution.
Sorry. Yeah, so the VIIRS has, well, again, VIIRS has higher spatial resolution. The actual spatial resolution depends on the specific product. So as we discussed today, so for aerosol optical depth, the spatial resolution is 750 meters. For the active fires I-band, the fire detections, it's 375 meters. So it varies by the specific product.
Yeah, the question was for aerosol optical depth, sorry.
Oh, for aerosol optical depth. Okay, sorry. So for aerosol optical depth, for VIIRS, it's 750 meters. For GO16, it's the ABI sensor. And for aerosol optical depth, that has 2 kilometer spatial resolution.
Okay, thank you. The next question is, the geostationary satellites can provide observations every few minutes for both aerosols and fire detection. True or false? So this is true, right? Amy already covered how the instruments and geostationary satellites have much better temporal resolution, and it's every few minutes. Entonces, esto es cierto. Esta la respuesta aquí era cierto, que es muy frecuente la resolución temporal. The next question is AOD from the satellites, does it represent aerosols close to the surface of the Earth? Close to the... Sí. Entonces, ya explicó la doctora Amy Huff que la profundidad óptica de los aerosoles representa la columna de los aerosoles, o sea, lo que es la cantidad total de partículas desde la superficie de la Tierra hasta la cima de la atmósfera, y por lo tanto entonces la respuesta aquí es falsa, porque representa no solo la carga de aerosoles cerca de la superficie de la Tierra, sino en toda la columna de la atmósfera. Y por esa razón puede o no estar correlacionado o tener una relación con la calidad de aire a nivel de superficie. La siguiente pregunta, el humo está compuesto de ambos, aerosoles y gases traza. En este seminario no estamos viendo los gases traza, pero por ejemplo también podemos detectar con satélites gases traza como el dióxido de nitrógeno, que también se puede emitir en grandes cantidades cuando hay incendios importantes. Este es un contaminante que sí vimos en los cursos anteriores. Pueden revisarlo si tienen interés en aprender más. El transporte del humo puede impactar la calidad de aire también lejos de la fuente, como ya hemos visto en las imágenes de hoy y otros días, que se pueden esparcer por una región muy grande. El instrumento VIIRS es un ejemplo de de un sensor activo, cierto o falso. Esto es falso. Los instrumentos activos son los que mandan energía del satélite hacia la Tierra y la energía se refleja y entonces el satélite detecta esa energía, pero ese no es el caso de instrumento VIIRS, que es un instrumento pasivo que está detectando la energía emitida por la Tierra y reflejada. El instrumento ABI del GOES 16 proporciona cobertura global solo en Sudamérica o en ambos Sudamérica y Norteamérica. Entonces, este instrumento está en el GOES 16, que como ya hemos visto es un satélite geoestacionario y que proporciona cobertura en lo que llamamos el sector de sector, que incluye ambos, Sudamérica y Norteamérica, y de hecho Centroamérica también, ¿no? Es lo que llamamos el sector de norte a sur. Entonces, la correcta respuesta es la tercera. Entonces, la profundidad óptica de los soles es un dato geofísico en este caso, la respuesta adecuada es tanto nivel 2 como nivel 3, ¿no? Porque los datos de nivel 1 son los datos que es lo que detecta el satélite, ¿no? Es la energía que detecta, entonces eso no es un dato geofísico todavía, es un dato crudo que no estamos viendo en este seminario. Eso se procesa para obtener los datos de nivel 2 o de nivel 3, dependiendo del tipo de grilla que tengamos. Y entonces los aerosoles están disponibles que son un dato geofísico tanto como de nivel 2 como de nivel 3. Y lo que hemos visto hasta ahora han sido los datos de nivel 2. Entonces, eso es el repaso de la tarea. Muchas gracias por entregarla, los que las habéis entregado, que yo creo que casi todo el mundo ha entregado. ¿Y alguna pregunta acerca de las respuestas a estas preguntas que podamos repasar ahora? También muchas gracias por entregar la tarea número 2, que creo que no todo el mundo la ha entregado todavía, no quedan todavía unos días para la fecha límite, pero no se olviden de la tarea número 2, que es simplemente mandar por el Google Drive, el Google Forms, los screen captures de las dos preguntas que se formulan en la tarea.